Chapter 3, Equilibrium of a Particle. Okay, class. Today we are going to talk about something very important in engineering. How to make sure things stay still and don't fall or move around when we don't want them to. Let's think about when you hold a bucket with a rope. If you just let it hang without moving, the bucket is happy, not going up or down, just staying still. This is called equilibrium. Engineers always need to make sure things like bridges, towers, or even toys don't suddenly move or break. When something is in equilibrium, it means all the pushes and pulls cancel each other out. First, we have to understand that if something is sitting still or moving smoothly, the total push or pull, what we call force on it, is zero. We write it like a little math sentence. Sum of forces equals zero. This is what makes the bucket not fly away or crash to the ground. It's also how we know how tight to pull on a rope or how strong a support has to be. Now, to make our life easier, engineers like to draw what's called a free body diagram. Imagine cutting something out from its surroundings, like cutting a photo of a swing from a picture. Then you draw little arrows on it to show all the pushes and pulls acting on it. It's like drawing where your friends are pulling you in a tug of war. This helps us see clearly which way the forces are going. There are a few common forces we always see. First, we have springs. Think about your toy Slinky. It stretches when you pull it. The more you pull, the harder it pulls back. This is called spring force. There's also cables, like ropes, which can only pull, never push, and they always pull in a straight line. Lastly, when something touches a smooth surface, like ice or a slide, the surface pushes up but doesn't grab sideways. That's called a normal force, just like when the floor pushes up your feet. After drawing our diagram, we use simple steps to count up all the pushes and pulls in the left-right direction, called x-axis, and the up-down direction, called y-axis. For everything to stay still, the total left-right force must be zero, and the total up-down force must also be zero. If we miss this up, things start moving or falling down. Sometimes we also work in three directions: sideways, forward-backward, and up-down, which are x, y, and z axis. Think about a drone flying in the air. It can move in any direction. We have to make sure in every direction the total forces cancel each other out. Let's see a simple example. Imagine a lamp hanging from two ropes. The lamp's weight pulls it down, but the ropes pull it up from two sides. Using our steps, we draw a diagram, we write the two force rules, we solve with simple math, and we find out exactly how hard each rope is pulling. If the ropes are not strong enough, they will snap, so we always have to check. Sometimes there are more complicated situations, like when springs are involved, or when something is connected with many ropes and pulleys. We just follow the same steps: draw, write, solve. Even if we guess a wrong direction for an unknown force, the math will give us a negative number, telling us the direction is actually the other way. This is very helpful. In summary, equilibrium helps us understand how to keep things from moving. We use free body diagrams to see all the forces, we make sure forces in every direction cancel out, and we use simple math to figure out unknowns. This is how engineers make sure our buildings, rides, and machines are safe and steady, just like you making sure your Lego tower doesn't topple over.